Okay, let's start. So, in the week 4 content, today for the week 4 content, we will discuss 6 questions, and these questions are related to transmissibility, and some questions are related to the viscous damping. Like this is the some transmissibility part we have considered in the week 3 content, and some part is in the week 4 content. Okay, so let's start to the presentation. And okay, so the first question is the if 50 kg laboratory experiment is to be mounted on a table in the laboratory, the table which is rigidly attached to the floor vibrating due to the operation of the other machinery. Measurement indicate that the floor acceleration amplitude is the 1.2 meter per second square and it's vibrated 100 hertz. And accurate use of the equipment require this to accelerate amplitude be limited to zero point 0.6. So what is the largest equivalent stiffness of the mounting of damping ratio zero point 0.1 that can be used to limit the acceleration amplitude to zero point 0.6 meter per second square, and what is the maximum deflection of the mounting in the meter? So you have given, like, you have given total vibration u double dot t is given to you 1.2, and the ground vibration, which is a limited vibration, equipment vibration, which is given you to the zero point 0.6. So you know what is the transmissibility? Transmissibility is the u total divided by the u equipment t. So you have given the transmissibility 1.2 divided by zero point 0.6. Sorry, that will be the reverse. Like u total is this and the floor vibration is this, so that will be the this. Zero point 0.6 by 1.2 is zero point 0.2. So can you calculate the stiffness? Like you have given the damping ratio, you have given the like the total acceleration limited to point 0.6 meter per second square, you have given the external frequency, so you have to calculate the stiffness. Am I audible to everyone? Am I audible to everyone? Is there any doubt in this question? If not, let us discuss. So in this part A, the transmissibility ratio, what is the transmissibility ratio? Whatever I have discussed here, that is a U total divided by U ground, or the in the acceleration term. This is in the displacement, but the transmissibility is same for the acceleration as well as the displacement. So this is the transmissibility U total, like the limited is the zero point 0.6, and this is the total, like the measurement indicate that the floor acceleration. Like consider this is a some floor and there is some equipment here. So for the floor vibration, it is vibrating 1.2, and in this response it is zero point 0.6 coming out. So we have to finding out, and there is a damping pads are there. So we have to find out that what is the stiffness of the damping pad. So with the damping ratio, with the transmissibility ratio, you can find out the transmissibility formula. As you have, if you have watched the video of the NPTEL course, then you will find that transmissibility is given by this formula. From this formula you can equate to this, and in this formula Xi is the damping ratio, it is the damping ratio, and this is the frequency ratio. Okay, so put the value zero point 0.2, and damping ratio is given to you 0.1. Damping ratio is given to you 0.1. So simplify this equation. Like first do the square both the side, and after squaring you will get a quadratic equation, fourth polynomial equation. And this equation if you solve you will get 4 root. For this equation you will get r1, r2, r2, r3 and r4. But the only real root, there is a one real root would be there, and there are the complex root, and another one is the, this is in the negative form, and this is in the real root positive, and these two are in the complex form. If you will solve this equation in the calculator you will get this. So for the real root, one real root which is r is equal to 1.758. Okay, if you have r is equal to 1.758, so what is your r is omega divided by omega n. Okay, so what is your omega? Omega is given to you 100 hertz. So can you convert it to the radian per second? So in the radian per second, to convert it to, that will be the 2 pi into 100. Okay, and the omega n is you have to find out. So that would become as a r is equal to 1.758 is equal to 2 pi into 100 divided by omega n. So from here you can find out the natural frequency. It is coming out to be 3.57 into 10 raised to power 2 radian per second. Okay. So now if you have the omega n, now you have to find out the stiffness. So what is your stiffness? Omega n is equal to square root k by m. So what is your stiffness? It would become as k is equal to m omega square. So that is the n. That would be the n. So from simply, and the m is given to you 50 kg, 50 kg. So when you simplify and solve this equation, you will get your stiffness. That is the one part in which you have to find out the stiffness of the system. Okay. Now we are moving to another part in which the thing is asked as what is the maximum deflection of a mounting deflection. So for the maximum static deflection can be calculated as u naught. Deflection can be given as u naught is equal to p naught by k into rd. And what is my p naught? In this case my p naught would be the m into ug double dot ug naught, and k I can write as a k, as I can write here like k is m omega n square. So m will be cancel out, and you, I will pre-multiply it with the omega square in the both upper both in the in the upper and the lower side. So that would be the omega square here, and that is omega square here, and the omega by omega, and what is your omega by omega n? R. So we will replace this as a r, and that is the omega square into rd. So you have the value of the r, you have rd, you have to, and the omega, and ground acceleration you have, which is ground acceleration given to you, which is limited to zero point 0.6, and rd is given, rd you can calculate, that is rd is 1 upon square root of 1 minus r square over whole square plus 2 xi r square. Okay, so rd when I calculate it comes out to be 0.47. Okay, so when you put the rd into u naught, that is your u naught. Sorry, UG naught is the 1.2 as given in the question. I was considering initially zero point 0.6. So that is your maximum deflection. Okay. Is there any doubt into this question in this question, or should I move to the another question? Let's move to the another question. In this question, an air conditioner weight is 1 kilonewton is given to you, and it driven by a motor at 500 rpm. Like the weight of the, like you have given weight W is equal to 1 kilonewton, or you can say mass converted to mass, and a motor which, that is the weight W, and omega is given to you 500 rpm. What is the required static deflection of the undamped isolator to achieve 80%? And let us, like, that is like air conditioner, and there is a like some isolator pads, it is attached to some isolator pads. Okay. So if it is this attached to a isolator pad, so what is, and the isolator is reduced like the deflection 80%. So you have to calculate the static deflection which is in the isolator for two cases, if the damping ratio is 0 or damping ratio is zero point 0.1. Okay. So for that, have you understood the question? Anyone? Have you understood the question? Anyone has any doubt? Like there is a air conditioner, and that is connected to the isolators, and that is a base. So due to isolator, like isolator, the response is reduced to the 80%. So how much response is transferred to the structure? Only 20%. Like transmissibility, what is transmissibility? Only 20%. So your transmissibility would be the zero point 0.2, because 80% response is reduced by the isolator. So if your transmissibility is zero point 0.2, so can you find out what is your static deflection of the isolator? Like damping is 0. So if the damping is 0, what would be your transmissibility? Like this is the same I have told you, like 80% response is reduced. So how much it retain? 20%. So ft divided by f naught is zero point 0.2, which is a transmissibility. So for an undamped isolator, which mean damping is 0, so transmissibility reduced to this. Else, transmissibility is equal to square root 1 plus 2 xi r square 1 minus r square over r square plus 2 r xi square. If you put damping as a 0, then this term diminishes, this term diminishes, so only what will left? 1 over 1 minus r square. So you have transversal t is equal to zero point 0.2. Can you find out what is the value of r? Can you give a try? Krishama, can you, are you able to understand the question?
Yes, sir.
So can you give a try to find out what is the value of r? Like first do the square on the both the sides. So that will be the zero point 0.2 square is equal to plus minus 1 over 1 minus r square square, or directly you can write it not squaring both the side, because there is a denominator only one term. So that will be zero point 0.2, and you taking under root this, so that will be 1 over 1 minus r square. Okay. So find out what is your value of r. This is simple, nothing. Like that would come out to be plus minus 1 minus r square 1 by point 2 is equal to 5. So the equation is become as a plus minus 1 minus r square is equal to 5. So take one time as a plus or one time as a minus, what value you get the r. Okay, so this is the same thing which I have written. So if first I have considered a plus sign sign, so that comes out to be r square is equal to minus 4. So that is comes out to be imaginary complex number. So that can't be my r value. Now I have to consider the negative sign. So if I consider the negative sign, I get the value of r is equal to 2.45. And if I have r is equal to 2.45, I can easily find out what is my natural frequency. R is equal to omega by omega n, and what is my omega is given to you 500 rpm. So with that, you can find out your omega n. If you convert it to multiply the 500 rpm to 2 pi by 60, so that will be your in the radian per second. So that is your omega n. If this is your omega n, now you can find out your stiffness. So the required static deflection can be obtained like F is equal to K into UST static deflection. So here the weight is 1 kilonewton. Weight is 1 kilonewton. So you have to find out like in terms of like the force, like the deflection is what is the deflection? UST divided by F by K. So F is given to you 1 kilonewton. You can find out first K. K you can find out as a m omega n square. So you have m, you have omega n, you have f, you can directly find out the UST. This is my UST static deflection 0.0214. Is there any doubt up to this point? Anyone?
No, sir.
Okay. In the second part, I have given the damping in the isolator. Initially, there was no damping. So now with the damping, ratio zero point 0.1, what is my transmissibility ratio formula? That is this square root of 1 plus 2 xi r whole square divided by 1 minus r square over square plus 2 xi r over square. So now with the same thing, like transmissibility is the zero point 0.2, only thing it changes that the damping ratio is the zero point 0.1. So now put the value of the damping ratio in this, and we have to again find out the what is your r value. So for this, I have put the value of R value damping ratio zero point 0.1 and the transmissibility, and simplifying these terms and rearrange this equation. So I got the value like the equation in the fourth order polynomial. If I solve this equation in the calculator by using calculator, you will get four roots, but only one root is the real root. Other two roots are two roots are only the two roots are the complex root, and the one root is the negative side. So only one root is the real and the positive, which is r is equal to 2.57. Now that is the same procedure. With this r is equal to 2.57, can you calculate the static deflection? Like in the previous case, with the r is equal to some value, I have calculated the static deflection. Can you give a try? Like first calculate the omega n. What would be your omega n with the damping ratio in the in this case? Can you find out? Like r is equal to given
20.37.
what? Can you again ask me?
Omega n is equal to 20.37.
Okay, omega n is the 20.37. Okay, like I have rounded it, round up. So that is the 20.4. So can you find out the static deflection with this? like F is equal to KX, KUST, and UST comes out to be F divided by K, and that would be the F is equal to M omega n square. F you can written as a mg m omega n square. If you will cancel out, so that would be g divided by omega n square. Simple. So if you have calculated, or like I will show you the answer, what is why deflected static deflection is comes out to be 0.0236. Are you getting this answer?
Yes, sir.
Okay. Up to these two questions, you have any doubt? If not, then I move to the another question, which is also related to the transmissibility, in which a simplified model of the vehicle suspension system is shown in the figure. If the vehicle is traveling at 100 km per hour over a road whose surface has a sinusoidal varying roughness with the spatial period of 4 meter, like this distance, like it is going to up to the 4 meter something, like constant, and then they determine the steady state magnification factor or the transmissibility for the vehicle absolute motion when the fully loaded and the when the empty. The mass of the vehicle is 1200 kilogram when the fully loaded and the 400 when the empty. The effective spring constant is 400 kilonewton per meter, and the damping factor is zero point 0.4 for the when the vehicle is fully loaded. Like first you read the question, like are you able to understand the question? Like this is also simple transmissibility question. Like in this I will show you how the transmissibility question comes out. Else this is the simple question, like this is the Z, that is the ground displacement, and this is the U, the vehicle displacement. So U divided by Z is equal to transmissibility, as you know. Or I will get the how the trans U by Z comes out to be transmissibility, I will show you in this question. So if you have given the U by Z is equal to transmissibility, so like you have to only just calculate the transmissibility for the both the cases. If the vehicle is fully loaded and if the vehicle is the empty. So you have given the mass for both the cases. The only thing you required is the damping ratio. For the fully loaded, damping ratio is given to you zero point 0.4. For the empty, you have to calculate what is the damping ratio for the empty. Okay, let us discuss how we calculate. Have you understood the question? Okay, so let's find out, like for this vehicle, like what is our differential equation? Like this is system, damper, and this is the vehicle, and that Z is this displacement and U is this. So only the thing will be changed in this damper and the stiffener, like that will be say change, like relative, and the acceleration would be the absolute total acceleration. And in this question you have given that the vehicle like the traveling is a geo, like in the sinusoidal. So and this amplitude is given to you Z. So what is my equation? Z is equal to zt equal to Z into sine omega t. Okay, so Z is equal to Z sine omega t. If you put the zt into this, like calculate what is your Z dot, like the this velocity, that would be Z into omega cos omega t. And the now use, like rearrange this equation. If you rearrange this equation, what is this equation? Mu double dot plus cu dot plus ku is equal to cz dot plus kz, and put this value in this Z dot. what the values in this. So by differential equation, like I have rearranged this equation same as like here, and if you put the value of zt, it will become like this: mu double dot plus cu dot plus ku is equal to kz sine omega t plus c z cos omega t. This is our z dot t. Now, if I consider, like, what is my formula of sine a plus b? Sine a plus b, what is sine a plus b? Sine a cos b, cos a sine b. Sine a cos b, cos a sine b. So if I consider, like I have termed the sine, like I have considered like kz as a cos theta and this term as a sine theta. So this would become as a, like, kz is I have considered as a some constant r cos theta, and the c z omega some constant r into sine theta. So that whole term would become as a r sine omega t plus theta. Okay, and I can get the value of r if I square this term and square this term and add them, then it would become as a r square into sine square theta plus cos square theta is equal to kz square plus cz omega square, and take this would become as a 1. So r values becomes out to be I square root of kz square plus cz omega square. Okay, so that is the you can take the z out, so that is the same thing. Have you understood how I get the this expression? Any doubt?
Yes. No.
Okay, so now this is the same differential equation, like I have solved in the, like if you read in the week 2 content or the week 3 content, like this is the same kind of equation in which only the multiplication factor change. Like if my equation was mu double dot cu dot plus ku is equal to some p naught into sine omega t, that was the equation. So only my p naught is this one. So my response is, this is the p naught. Okay, so for this equation, what is my response? U is equal to u naught ust rd into sine omega t plus theta minus phi. So for the maximum, we consider like this is a when, this is 1 for the absolute maximum response. So what become my ust? Ust become as a p naught by k into rd. And what is my p naught? P naught is this magnification factor, or this you can call it as a loading factor something. So if you put this value at here at the place of the p naught, you will get the, like this is by the p naught, this is k, p naught by k, this is my rd. Okay, if I rearrange the term, like I have taken z into this below this, and I write like k is equal to m omega square, and then I taken out k from here. If you will rearrange or solve this equation, k is equal to m omega n square, c is equal to, you will write 2 xi m omega n something, and if you rearrange the term, then this will come out to. And this is what? This is your transmissibility. So for the vehicle, like the in the sinusoidal movement of the vehicle in the sinusoidal wave, so this is the also the case of the transmissibility. Okay, so in this case we have to find out the transmissibility m. So here the magnification factor or the m transmissibility is this. So for this we have two cases, like the vehicle is empty or the vehicle is fully loaded. So for the fully loaded, we have all the things like whatever we required. We have the, like the omega n, we have the damping ratio. But for the empty vehicle, we have not the damping ratio. So we have to calculate what is our damping ratio. Okay. So for the speed is like given as 100 kilometer per hour. So we converted it into the meter per second. multiply it with the 5 by 18. Spatial distance is 4 meter, so that the spatial period, what is my period, 4 by 27.78, that would be the 0.144 second. And the frequency 2 pi by tn, that is the 43.63, that is by the omega. Okay, the stiffness of the system is given to you 400 kilonewton per meter, and mass is given to you 400 kg. So you can find out what is your, for the for the empty vehicle and the fully loaded. So you can find out your what is your like a natural period, natural frequency omega n, for the empty k by me under root, and for the fully loaded k by mf, that is a 31.62, and that is 18.25. Now we have to find out the damping ratio. For the fully loaded vehicle, the damping ratio is a zero point 0.4. So what is the expression for the damping? Damping is the C divided by the C critical, and where the C critical can be written as a 2 under root Km, and what is our constant? Stiffness, and the like the for the any vehicle like this term is varying, like in this case damping ratio and the mass, but this system is constant. Like for any vehicle, like stiffness is always constant, mass can be vary, but the stiffness is constant. So that is the case, like if we have a xi under root m is constant, so means xi 1 m1 is equal to xi 2 under root m2. Okay, this is the case. So with the help of the fully, like we have the these two value, and we have the me value, we can calculate our empty ratio, empty like the damping value for the empty vehicle. So that is comes out to be 0.693. Are you understanding up to this? Have you understood? Any doubt?
No, sir.
Okay, now you have all the values. You have the natural frequency, you have the external frequency or the forcing frequency, you have damping ratio for the fully loaded and the empty, and now you can calculate the magnification factor. For the empty vehicle, I have put the value of the damping ratio this 0.693, whatever we get, and the frequency is the natural frequency is the 31.62, that is the omega n, that is the external frequency omega, and that is the empty. So that transmissibility comes out to be 1.02. And for the fully loaded vehicle, same, like we have to change the only the damping ratio and the natural frequency. So that is comes out to be 0.424. And this is transmissibility for the empty vehicle, and this transmissibility, oh, sorry, this is the for the fully loaded, and this is for the empty vehicle. Okay, is there any doubt into this? Okay, now if you have not any doubt, now let's move to the another question, which is a simply like a expression type question. Like now we are covering the some question related to the damping, viscous damping. Okay, these were the questions related to the some transmissibility. Now we have, this is the like this question 4 is some related to the you can say like the one line question. You have given a energy dissipate by the viscous damping during a cycle of motion of an STF system due to force is E. Determine what factor of the energy dissipate during a cycle will change if the forcing frequency is double. Like in the first case for the E, your forcing frequency is omega and your amplitude is a u naught. If my forcing frequency is double to omega, so my new energy, like the energy dissipate in the viscous damper, my omega to omega, and the displacement amplitude of the system is heaven due to if we like doubling the forcing frequency, so my u naught is u naught by 2. So can you calculate what is when the new damping, like the new energy dissipation? Do you know what is the formula for the energy dissipation due to the motion in the one cycle? Anybody? Okay, if not, like that is also like that the derivation also discussed in the week 4 content, in the week 4 content lecture 2 module 2 if you will go. So in this I am using the direct formula for the dissipation of the energy. Ed is comes out to be, this is the pi c omega square into u naught. So now can you find out, if my omega is a 2 omega and u naught is a u naught by 2, what would be my new energy, what factor? Can you find out the factor? It is a simple calculation. Anyone? Anyone can you give a try? Let's find the new energy, like PD new, in which omega is become as a 2 omega and the u naught become as a u naught by 2. So that become energy, if you solve that become as a pi c omega into u naught square divided by 2. So that factor is comes out to be 1 by 2. Any doubt in this question? Anyone? In the next question, we will also discuss the damping, but in this we will find out the derivation of this, and there is a energy dissipation with other mode. So a derivation for this also. Any doubt up to this?
No, sir.
Okay. So you have given a question like a block of mass 1 kg is attached to a spring of stiffness is given to you 3 into 10 raised to power 5 Newton per meter, and the block is displaced 20 mm from a equilibrium and the release from the rest. The block is in the fluid where the drag force is given by the Ft is equal to CD U dot and the in the mod U dot, with drag coefficient CD is given as a 0.86 Newton second square per meter. So approximate, we have to find out the approximate number of the cycle before the amplitude is reduced to 15. Like we have a response, like we have given initial displacement 20, like this is says 20 mm, and due to the this drag force energy is dissipating, and at what number of cycle my amplitude is reduced to 15. So for this I have to find out what is my damping ratio first. Like this is a kind of logarithmic decrement. So for the logarithmic decrement, like logarithmic decrement, what is ln over ui divided by ui plus 1 is equal to 2 pi xi n. So for that number of cycle or the response less than 15 mm, I have to find out what is my damping ratio xi. So for finding out the damping ratio, I have to find out what is my c. From the c I can find out the damping ratio. Have you understood the question? Like what is our like motto in this find out the question, what we have to find out? Okay, let's go with this. So in this, the energy dissipation by the viscous damping in one cycle of the harmonic motion is given by the, like the energy dissipation is the in the one cycle ftx. Okay, so fdx, how can I written this ed? Like the energy dissipation is the in the one cycle, my one cycle is 0 to 2 pi by omega n or the tn t1, and that is the ftx. So can you tell me like how I convert this equation to this f dot u dot? You know what is our damping force? Let us leave it like I write in it written as a ft. Dx is like the displacement is u dot into dt. Okay, so like replace dx to this term. Okay, and damping force, what is my damping force in the differential equation? That is cu dot, generally we are using. So I replace this with this cu dot. And what is my u value response? U is equal to u naught sin omega t is my something response. So if I differentiate it, it will comes out to be u naught omega cos omega t. And if I put this value in this equation, u dot value in this equation, my equation is become this. Like first, like this is my equation. Like if I put the ft here, and then for the u dot I will put the equation. So my final equation is this. So can you integrate this? Like if you integrate, you will get whatever, you will get the result as whatever I use in the previous question. So do you know, if a equation is given to you 0 to pi by 4, pi by 2, and the term is the cos n x dx, so what is the solution for this? If you have read n minus 1, n minus 3, so on, and in the below it is n minus 2, n minus 4. This is when the my power is the odd. If the power is even, then I will multiply it with the pi by 2. So here the power is 2. So this is the full cycle, like a whole cycle I have to convert it to pi by 2. So this is the, like cos is the, like the even function. So you can write it as a 4 into 0 pi by 2 into omega. If you divide it by the this c u naught square omega square, and that is the cos square omega t dt. Okay, if you will do this for the for even power, that is the 4 into c u naught square, and that is divided in the omega, so that one omega is cancelled out with this, that is omega. And that can be written as a, that is the n minus 1, that is the 2 minus 1, and further term will be diminishes, and in the bottom that will be a 2, and multiply with the pi by 2. So these two are cancel out, so that will become as a pi c omega into u naught square. Okay, understood up to this, like how I have done the integral?
Yes, sir.
Like you can solve it like simply as you know, like using the integral by parts, but that is the simplest form, like how you solve this equation. Now the another form of energy is introduced by the drag force, by the fluid in the drag force. So that form, that form is like given to you ft cd u dot in the mod u dot. So same, you have to do nothing. Like in the first case you have to consider ft is equal to cu dot. Now in the place of the cu dot, you have to use this one, only this, and nothing you have to you need not to do nothing, only do this. So if you consider this, so my equation will become this. Like this is my ft, and this is my the previous part, this one. So if you rearrange the terms, that would become this. And if you take the mode as a positive, like here I am taking positive, so that equation become as a even function. So that equation is equal this. And for the even function, I have doing the same thing whatever I have done previously. So here the term is the cube terms. So for the cube term, what is my, like I will not need to multiply with the pi by 2, only like the is the 3, so that would be 3 minus 1, other terms are diminishes, so that will be 3 into 3 minus 2, so that would become 2 by 3. Okay, so my energies become this. Now if I compare both the energies, viscous damping and the energy due to the drag force, so this is my equation. So from here I can find out what is the value of my viscous damping C value. So you have given the CD, you have given the U naught is the 20, and you have given the omega also. Given na? It is given to you omega also. That you can find out, like you have given the mass and the stiffness. So you can find out this CD is equal to 0.86, and omega is the 3 into 10 raised to power 5 divided by the 1, that comes out to be this. C is become to you. The damping is become in terms of the 399.83. So your damping ratio, what is your damping ratio? C divided by the C critical. So your C is this 399.83 U naught, and the C critical is 2 into 1 into 3 into 10 raised to power 5. So that is become as a 0.365 U naught. So if from the logarithmic decrement, delta is equal to 2 pi xi. So delta is equal to 2 pi xi, and this is your ln un divided by the un plus 1, and the xi value is given to you 0.365 into u naught. Or if you will rearrange or solve this, that will become 2.29. So u naught is the initial amplitude at the beginning of the cycle, which is not constant. So you have given u naught as a 20. So if you have given the u naught or the un given to 20, so at the end of the cycle, what is your un plus 1? You can calculate. Okay. Then after getting the first cycle, by using this un plus 1, this term, some letters, that is comes out to un plus 1 comes out to be 18. If you put 18 here, 18 here, you can get the another cycle, what is your response after the end of that cycle. So that you can, this way you can proceed in this question. Un divided by the un plus 1, so ln goes to the this exponential terms. So this becomes as a un plus 1 un. And now this is the table, like in the at the beginning of your cycle, what is your amplitude? 20. If I put the 20 here and here, I get the un plus 1 after the cycle 19.4. If I use this as a un in the for the next cycle, I get this 18, this un. Again I will use this, I will get this, like doing the same iterative process. So in the question asked like the how much number of cycle it take when the response is reaches to the 15 mm, so that is around this eighth cycle, like up to eighth cycle. In the eighth cycle, that goes to response become to the 15 mm. Okay, is there any doubt in this question? I know this is a like hectic question, some like you are thinking how these things are coming. So if you will do practice by yourself and understanding by yourself, like you, if you have any doubt, you can ask here. Any doubt? Anyone? Should I move to next question?
Yes, sir.
Okay, so this question is the last question. This is a very simple question actually, like transmissibility related question again, in which the support is in the motion, like a 35 kg block is connected to the spring of stiffness 1.4 into 10 raised to power 6 in parallel with the damper, which coefficient is given to you 1.8 into 10 raised to power, like this is a support, a spring, a dashboard damper is connected, a mass is given to you, stiffness is given to you, damping is given to you, and the motion is this, and this also, this support has some motion like this. The support is given a harmonic displacement of amplitude 10 mm. Let us, the harmonic displacement is given to you, this block is the 10 sine omega t, and where omega is given to you 35 hertz. So the motion of the support is given to you. So we have to find out what is the steady state amplitude of the absolute displacement of the block. So this is the case of the again transmissibility, like the motion of this is given the absolute, like the response u naught is given to you 10 mm, and this is the u total, so that would become ut divided by the u naught is equal to transmissibility. So can you give a try, like you have given the mass, stiffness, so with that you can find out your omega n. You have given that damping coefficient c, with the help of c you can find out our damping ratio, and the omega is given to you 35 hertz, that means 2 pi into 35, so that is come around uh, 200 something nearly. So can you find out ut? Is there any doubt in this, like what you have to find out? Can you give a try or should I discuss? Anyone? Okay, let us discuss. Natural frequency of the system omega n, can you find out? Square root of k by m, that is comes out to be 200 radian per second, and the damping ratio c by cr. So cr is 2m omega n, critical damping, so that is comes out to be 1.8 into 10 raised to power 3 divided by 2 into 35 into 200, so that damping ratio comes out to be 0.1285, and the frequency ratio is r, which is omega divided by the omega n, so that is coming out to be 2 pi into 35 divided by 200, so that is comes out to be 1.1. So that is given to you, you can find out transmissibility directly. So transmissibility ratio, that is square root of this expression 1 plus 2 r j r square, and in the below that is the 1 minus r square square plus 2 j r square. So if I put the xi value damping as a 0.12 r 1.1, then simply I would be able to find out the transmissibility comes out to be 2.9 or 4. Now I know what is my UST or U naught is 10 mm given in the question. So that is my absolute displacement, total displacement of the globe. Now in the part B, it is asked you to relative displacement. So the relative displacement is the U minus ka U naught, U static. So in the previous equation, like for the transmissibility, when we find the transmissibility, we write the equation as a C U dot minus, like in the previous we write it as Z. Here I am using U naught. So if I replace u as ur, so that will become as a ur double dot. This is become a ur dot. This will become ur, and in this ur term, like u will become as a ur plus u naught. So in the this side that would become mu naught double dot. Okay. Not ur, not u naught. This is u only. So this u is given as the u naught into sine omega t. So u double dot comes out to be u naught omega square minus sine omega t. So if you put this value here, this, so my p will become p naught or p minus ka m into omega square into u naught. Okay. So what is my maximum displacement given to you? U divided by p naught by k into rd. So p naught is given as a m omega square u naught divided by k into rd. So if I write it as a m omega n square k, that will cancel out, and that become u naught into omega square into rd. Sorry, that will omega square by omega n square. That become r square. So simple multiply rd with the r square, you will get the response. Like whatever like this. This is the response I get, like r square into rd, and this us, or in this case I have written the us, or you can write it as a u naught. So if you calculate this, you will get the ur divided by us comes out to be 3.43. So from this, the relative displacement of the block is comes out to be us multiply with the 3.43, and us given to you 10 mm, so that comes out to be 34.3 mm. Okay. Is there any doubt in the all questions, like in the last six questions, or in, like, are you able to doing the assignments like easily? Any doubt in the assignments related queries? Any doubt? Am I audible? Is there anyone?
Yes, sir.
So is there any doubt?
Uh, no, sir.
Okay, if you have not doubt, or if you have any doubt in further, you can ask through the discussion form, or you can ask in the next live session which will held on the next Tuesday. Okay.
Okay, sir.
Thank you.
Thank you, sir.
So I am ending this session here.